Myself, Professor Radharani Das, Dean, Department of Chemical Engineering. My topic to discuss is the convective heat transfer and its application in the various heat transfer area. Convective heat transfer process is the collective movement of and the group of molecules within the fluid. In convective heat transfer of heat takes place from the hotter to the colder body by the movement of the fluid particles through the medium, and it is characterized as the free or the natural convection and the forced convection. In natural convection, the fluid motion is caused due to the density differences produced by the temperature gradient. A stagnant layer of the fluid in contact with the hot body receives energy by the conduction, resulting increase of the internal energy of the fluid particles. And due to the rise of the temperature, the lighter fluid particles move upward to a region of the low temperature. Simultaneously, the cold, heavier particles move downward to fill the space vacated by the warm fluids. Thus, the circulation pattern gets up in the fluid and it is called the convection currents. In the forced convection, fluid is forced to flow along the solid surface by means of external energy provided by the pump, fan or other compressor. Examples of the forced convection are the cooling of internal combustion engine, air conditioning installations, nuclear reactions, heat exchanger, condenser and the other number of the process equipments. In the forced convection, exchange of the heat always greater than that of the free convection. Now regarding the heat transfer coefficients, the heat transfer rate in the convection is directly proportional to the surface area and the temperature gradient. The proportionality constant is called the heat transfer coefficient. Mathematically, Q is the rate of heat transfer is the proportional to capital A, that is the surface area, and the temperature gradient Ts minus To. So Q is equal to small h into capital A into Th minus T0, and the small h is indicated as the heat transfer coefficient. It may be defined as the heat flux per unit temperature gradient. So small h can be written as the small q by delta T. So heat transfer coefficient small h is a function of fluid flow, properties of the fluid, surface conditions and the thermal conductivities. Now in case of the principle of the heat flow in the fluids, a general equipment for the heat exchange is the heat exchanger. It may be cell and tube type or the double pipe type. Double pipe heat exchangers are very simple. Here the exchange of the heat occurs between the two fluids. One is cold and another is hot. And heat transfer always takes place from the hotter fluid to cooler fluid. And heat transfer process, the temperature difference vary with the position and the time. According to the direction, three types of the flow may be arranged. One is the parallel, another is the counter, and third one is the cross flow. In the parallel flow, the fluid can be arranged so that both fluid enters at the one end and leaves from the other end. And the parallel flow is rarely used in the heat exchangers because it is not possible to bring the exit temperature of the one fluid nearly to the entrance temperature of the other. Thus, the parallel flow is used in some special situations where it is necessary to limit the maximum temperature of the cold fluid or where it is important to change the temperature of at least one fluid very rapidly. In parallel flow, heat can be transferred lesser than the counter current flow. This is the figure of the parallel flow heat exchanger, double pipe type, and this is the temperature profile, which is given that the fluid flows takes place in a same direction, but at each point there is a different temperature gradient delta T. In counter current flow, fluid enters at the two different ends of the exchanger and the flows in the opposite directions through the unit. It is called the counter current flow. So this type of the flow is the commonly used in the chemical industries, and it is always advantageous than the flow current or the parallel flow. And this is the figure of the counter current flow, where the two fluid, one is the hot and the cold fluid is the flowing. Hot fluid is flowing in the inner pipe and the colder fluid is the outer section. And it is noted that the TH2 is the highest temperature of the hot fluid, which is the entering temperature, and exit temperature is the capital T small h1, and the entrance temperature of the cold fluid is given by the TC1, and it is leaving as the TC2. This is the schematic diagram of the cross current flow. There are which flows across the banks of the tubes at the right angles to the axis of the tubes. Now the relation between the heat flow rate and the LMTD. So what is LMTD? LMTD is the log mean temperature difference. We have seen in the diagram 1 and the 2 that delta T1 and the delta T2 are the approach temperature. Now what is the LMTD? LMTD is the delta T1 minus delta T2 divided by ln of delta T1 by delta T2. So this equation can be written as a correlation. Capital Q, that is the total heat flow, is equal to capital U into A into LMTD. So capital U is the overall heat transfer coefficient and capital A is the surface area and delta T is the log mean temperature difference. Now what is the overall heat transfer coefficient? In a heat exchanger, driving force is given by TH minus TC, that is the delta T. But the delta T also varies considerably from the point to point along the tube. Since the heat flux is the proportional to the delta T, the flux also varies with the tube length. Thus, it is necessary to stand with the differential equation by focusing attention on a differential area dA, through which a differential dQ occurs under the local driving force delta T. Thus, the local flux is given by dQ by dA, that is equal to capital U into delta T, and delta T is equal to TH minus TC, that is the differences between the hot fluid temperature and the cold fluid temperature. And capital U is defined as the local overall heat transfer coefficient. Now, considering AO and the AI are the outside and the inside area of a tube, and UO and UI are the overall heat transfer coefficients of the respective surfaces, then the relation between overall heat transfer coefficient capital U and the area can be related as UO by UI is equal to D of AI by DAO, that is the capital DI by DO, that is the internal diameter of the pipe divided by external dia, that is the outside dia of the pipe. This figure 3 shows a schematic diagram of a cross section of the double pipe heat exchanger, where the inner pipe radius, internal radius is equal to small ri, and small ro is the outer radius of the inner pipe. Hi is the heat transfer coefficient inside in the inner pipe, and Ho is the outside heat transfer coefficient of the inner pipe. Here the hot fluid temperature is the capital Ti, which is greater than that of the capital Tu, that is the outer fluid. And this is also the heat transfer between the fluid separated by a plane wall. If I take just one section of an inner pipe and place vertically, then this is the picture where it explains that the warm fluid is in the left hand side and the colder fluid is in the right hand side, and wall is the metallic wall with the thickness small l, and this is the temperature profile, that is the capital T1 A, B, C, D. From this picture Let us consider the inner and the outer radius of the inner pipe of a double pipe heat exchanger at the small Ri and the small Ro respectively. Corresponding heat transfer coefficients are the Hi and the Ho, and the length of the pipe is capital L, and the inner wall temperature is capital Twi, and the outer wall temperature is capital Two, and the bulk fluid temperature is Ti is greater than To. So the rate of heat transfer from the hot fluid to the inner wall surface at the steady state is given by, that is the rate of heat transfer from the hot fluid to the wall is capital Q1. Capital Q1 is related as small h1 into capital A into capital T1 minus TW1, where the rate of the heat transfer through the wall is given by capital QW, that is given by Km, that is the conductivity of the metal of the pipe, capital A is the surface area, and the driving force is the TW1 minus TW2. And the rate of heat transfer from the wall to the cold fluid is given by small h2 into capital A into TW2 minus T2. So because heat transfer is taking place at the steady state condition through a constrained area, so we can relate this equation as capital Q1 is equal to QW is equal to Q2 is equal to Q. So therefore T1 minus TW1 is equal to capital Q by AH1, and TW1 minus TW2 is equal to capital Q by A into KW by small n, and the TW2 minus T2, that is the transfer of the heat from the outer wall of the inner pipe to the cold fluid is given by capital Q by AH2. So if I consider these three equations, then adding these equations we can get that total temperature profile, that is the T1 minus T2 is equal to Q by capital A plus in the bracket 1 by H1 plus 1 by KW by L plus 1 by H2. That means capital Q by UA, where U is the heat transfer coefficient, and 1 by capital U is equal to 1 by H1 plus 1 by KW by L and 1 by H2. And this equation can be written as capital Q is equal to capital U into A into delta T, and total thermal resistance is given by 1 by capital U into A. And this equation can also be written as in the relation between the temperature of the inner wall and the outer wall, the Q by A1 H1 and TWI minus TO is equal to capital Q by 2 pi L KW by ln of RO by RI, and TW minus T2, that is equal to Q by AO into HO, where the AI is equal to 2 pi RIL, area of the heat transfer based on the inner radius of the inner pipe, and AO is equal to 2 pi R0 capital L, that is the area of the heat transfer based on the outer radius of the inner pipe. So adding these equations, three equations, we can rearrange this equation as the capital Q is equal to delta T, that is the Ti minus To, that is the inner temperature minus outer temperature, divided by 1 by AIHI plus ln of RO by RI divided by 2 pi KWL plus 1 by AOHO. Now what is the significance of the capital UO and the capital UI? Capital UI is equal to 1 by HI plus AI ln RO RI divided by 2 pi KWL plus AI by AOHO. And if I simplify this equation, we will get that 1 by HI plus RI into ln RO by RI divided by KW plus that is the Ri by ROHO. This is the UI, that is the overall heat transfer coefficient based on the inside area. Similarly, we can explain the equation for the overall heat transfer coefficient based on the outside area as this equation stated here, that is the 1 by Rho by RIHI plus Rho into ln Rho by Ri by Kw plus 1 by HO. So simplifying this equation, we can correlate this total equation as capital Q is equal to UIAI into delta T, that is equal to UOAO into delta T. Yeah, what are the practical significance of the UO and the UI? For a thin pipe, the thickness of the pipe may be very insignificant. Thus, outer dia of the pipe is nearly equal to the inner dia of the heat. And therefore, the ratio of the outer dia and the inner dia is equal to almost 1. And the ratio of the thickness to the thermal conductivity value, which is fairly high for the metallic case, will be very low comparable to the other terms of the following equation. So, thus the overall heat transfer coefficient and the local heat transfer coefficient may be correlated as 1 by capital U is equal to 1 by capital UO is equal to 1 by capital UI is equal to 1 by HO plus 1 by HI. So, where the HO and the HI are the outside and the inside free coefficients. Next, the determination of the local heat transfer coefficient, that is the small hi and the small ho. The local heat transfer coefficient may be defined as the ratio of the local heat flux and the total temperature difference as stated in the equation number 6. That is the small h is equal to dq by dA, that is the heat flux, divided by T minus TW, where dq by dA is equal to local heat flux based on the area in contact with the fluid, T is the local average temperature of the fluid, and TW is equal to temperature of the wall in contact with the fluid. So the second expression for the small h is derived from the assumption that there is no velocity fluctuation normal to the wall at the surface of the wall. Therefore, dq by dA is equal to minus k into dt by dy wall. Substituting the equation, the value dq by dA from the equation 6, we get the equation number 7, and the final expression should be small h is equal to minus k into dt by dy into w divided by T minus TW, and the multiplying both sides by the d by k, d is the diameter of the pipe and k is the thermal conductivity, we get the left hand side as a nozzle number. So nozzle number is equal to d into minus k dt by dy wall divided by T minus TW. So if we rearrange, you can start the dt by dy at the wall divided by T minus TW by capital T. So physical significance of the nozzle number will be given as the temperature gradient at the wall by average temperature gradient. And determination of the heat transfer coefficient for the designing purposes, if we go to design the double pipe heat exchanger or the selective heat exchanger, it is very easy to find out the small h, small hi, small ho using the nozzle equation, which using the Dietz-Botter equation, which is given by the nozzle number is equal to 0.023, NRE to the power 0.8 and Prandtl number to the power 0.3 to 0.4, that is given in the equation number 11, where the nozzle number is d by k, NRE is equal to d0 by mu, and the Prandtl number is equal to mu into Cp by the k. And in case of the laminar flow, these Dietz-Botter equation, in place of the Dietz-Botter equation, we should use the Sirat equation, which is given by the nozzle number is equal to 0.023, Reynolds number into Prandtl number whole to the power 1 by 3, and d by L to the power 1 by 3. That is the equation number 12, where d is the diameter of the pipe and L is equal to length of the pipe. So, importance of the heat transfer coefficient small h for the determination of the critical insulation thickness. We can explain that the considering insulated pipe vessel, where pipe or vessel, there are two major resistances act in the series. One is for the layer of the insulation and other is offered by the gas film on the outside of the vessel. Here two opposite factors on the rate of heat transfer come into play. When the insulation thickness on the pipe increases, with the increase of the insulation thickness, surface area also increases, which increases the loss of the heat due to the convective heat transfer. Again, conductive heat transfer decreases, so with the increase of the insulation thickness, heat transfer loss is there. Thus, as a result, overall heat loss increases, first reaches a maximum at the critical insulation thickness and then decreases, which is given in the picture 5. This is the relation. If we increase the outer radius of the insulation to the x-axis, it is find that the first the heat transfer loss is increases, it goes the maximum, then decreases gradually up to a certain limit. And this is the schematic diagram of the insulated pipe having the insulation outside the wall and the fluid flows in the inside fluid pipe. And from these two diagrams, considering the inner radius of the layer of the insulation and the corresponding temperature as Ri and the Ti respectively, the outer radius of the insulation and the ambient temperature are Ro and the To. The convective heat transfer coefficient inside and outside of the insulation is Hi and the Ho. Conductivity of the insulating material, the Kc, assuming the Hi is very large compared to the Ho, we get that final expression, the capital Q is equal to driving force divided by ln of Ro by Ri divided by 2 pi KLC plus 1 by AOHO. So if we rearrange this expression and take the differentiation of the outer radius respect to outer radius, we get the final expression as the minus 2 pi L delta T into 1 by KCHO minus 1 by HO Ro square divided by ln of Ro by Ri Kc plus 1 by ROHO is equal to 0. That is the for the insulated pipe. So if I want to know the critical radius, you have to consider this expression as a 0, and from that equation we get that RC, that is the critical radius, should be Kc by HO. Kc is the thermal conductivity, HO is the outside film heat transfer coefficient. Next. If the second derivative of the d2q by dr square, that is with respect to the outer radius, second derivative is negative, it gives the condition for the maximum rate of heat transfer. The value of the Ro minus Rc, that is the outer radius of insulation minus critical radius, is called the critical insulation thickness. When an insulation is applied on the steam pipe, its thickness should be always above the critical value. But for the insulation of the electrical wire, the insulation thickness should be very near to the critical value, show that heat loss is the maximum. So when the value of the Ro minus Rc becomes negative, it means that the critical insulation thickness does not exist for this. Now we can use the heat transfer coefficient for the designing of the double pipe heat exchanger purposes. It is very easy. For the double pipe heat exchanger, the first step is to calculate the data, physical data, and these data can be tabulated in such a way that we get it very easily. and this is the double pipe heat exchanger, one double pipe heat exchanger schematic diagram. For the designing purposes, for designing purposes, first step is the data collection. That is the flow rate for the hot fluid and the cold fluid, inlet temperature hot fluid cold fluid, outlet temperature hot fluid cold fluid, specific heat hot fluid cold fluid, and the conductivity, viscosity, and the density or the specific gravity of the fluid we have to know first. Then we have to go for the rate of heat flow, that is the heat load calculation. Heat duty or the total heat load can be related as the W into Cph into T1 minus T2 is equal to small w into Cpc into T2 minus T1. That is the heat lost by the hot fluid should be heat gained by the cold fluid. Both should be same. Now for the calculation of the LMTD, we have to know the approach temperature, hot end and the cold end. If the hot end approach temperature is delta T1 and the delta T2 is the cold end temperature, then we can calculate the total LMTD is equal to T1 minus T2 divided by ln of T1 by T2, and relation between the heat load and the LMTD is that Q is equal to UD into capital A into LMTD, and UD is the overall design coefficient. From the theoretical knowledge, we have to consider this, and the total surface area can be calculated as the capital A is equal to Q by UD into LMTD. Now calculation of the HO and the HIO, that can be calculated by the by calculating the first the mass flow rate and the velocity flow profile, velocity flow rate, and the Reynolds number at the pipe shed in the cell side, and from that we can calculate the J's, the and from the graph given in the Kern or any good heat exchanger books, and we can calculate the Prandtl number, and then that can be related using the Didas-Boder equation or this equation Kc into Jh into P to the power 1/3 by D, and from that we can calculate the HIO, that is the HI into Di by Do, and for the correction of the heat transfer coefficient you have to multiply this by the mu V by the mu W, that is the viscosity of the fluid at the bulk and at the wall. And cell side, similarly we can calculate the HO, that is the heat transfer coefficient of the cold fluid, and after that we can calculate the number of the heat exchanger is needed, double pipe heat exchanger is needed. Before that we have to calculate the RD, that is the dart factor, and dart factor is, there is a relation UC is equal to HIO by into HO divided by HIO plus HO, and 1 by UD is equal to 1 by UC plus RD, and RD can be calculated, that is the dart factor is equal to 1 by UD minus 1 by UC, and we have to check that whether the RD value that the calculated always should be greater than desired RD by the partition, and if it is satisfied, then the design of the heat exchanger can be completed. Now for the calculation of the total surface area, you can go for the capital A is equal to capital Q by UD into LMTD using the equation number 6, and then number of hairpin can be calculated by total surface area divided by pi dl, where d is the diameter of inner pipe and length is the L assumed by E for the designing purposes in the field. So number, if we know the hairpin, that can be connected in the series like this picture that can be given about the, yes, this is the 2 hairpin double pipe heat exchanger is just extended added in series 1 by 1. So this is the today's concept, and the books we have consulted is the Heat Transfer Principle and Application by Professor B.K. Datta, and the Unit Operation of the Chemical Engineering by the McCabe and the Smith, and the Peter Harriet and the process heat transfer by D. Kuker. So thank you all for your kind presence.